In the official narrative, the 19th century was an age of industrial revolution. Steam engines, railways, and canals transformed isolated communities into connected nations. Engineers worked with slide rules and determination, building infrastructure that would serve generations. It's a story of human ingenuity, ambition, and progress. But the Erie Canal, completed in 1825, moved 400,000 cubic meters of earth before steam-powered excavators existed. The project employed 9,000 workers across 363 miles of wilderness, maintaining grade tolerances that modern surveyors find remarkable for an era relying on basic transits and spirit levels. The timeline compresses strangely. Canal systems across multiple continents. Railway networks appearing in coordinated bursts. Road grids that anticipated population centers that wouldn't exist for decades. The precision wasn't just impressive. It was consistent. Before we continue, a necessary clarification. This is not a conspiracy documentary. What follows is an examination of historical infrastructure through the lens of timing, scale, and technical execution. Multiple explanations exist for every pattern presented here. The official historical record provides answers. Alternative interpretations offer others. This script presents observations and invites you to consider them within whatever framework makes sense to you. Now back to those canals. The Rideau Canal in Canada, finished in 1832, spans 202 kilometers through bedrock and swampland. It required 47 locks, each hand-cut from stone, fitted with tolerances tight enough that many still operate with their original mechanisms nearly 2 centuries later. The project took 6 years. The workforce was primarily Irish immigrants using hand tools. The engineering specifications were military grade. Colonel John By designed the canal to move gunboats and frigates between Montreal and Lake Ontario, bypassing the American-controlled St. Lawrence River. The locks were sized for vessels that didn't yet exist in Canadian service. The width, depth, and turning basins anticipated a scale of maritime traffic the region wouldn't see for 50 years. This wasn't unique. In Britain, the canal system reached its peak between 1790 and 1830. Over 4,000 miles of artificial waterways crisscrossed the island, connecting industrial centers, ports, and agricultural regions with mathematical precision. The Pontcysyllt Aqueduct in Wales, completed in 1805, carries canal traffic 126 feet above the River Dee on iron arches that still bear full loads today. The engineering required understanding of materials, stress distribution, and hydraulic principles that weren't supposed to be formalized for another generation. Thomas Telford, the aqueduct's designer, had formal training as a stonemason. His leap to designing cast iron spans of unprecedented scale happened, according to records, through self-education and intuition. The pattern appears across infrastructure types. In Russia, the Catherine Canal system connected the Volga Basin to the Baltic Sea by 1810, moving cargo across 1,100 kilometers through terrain that defeated Napoleon's armies. The locks, embankments, and reservoirs were built during a period when Russia was fighting multiple wars, experiencing political upheaval, and managing a largely feudal economy. Yet the infrastructure quality matches its Western European counterparts. The tolerances are similar. The engineering solutions mirror each other despite limited technical communication between regions. The timeline of completion clusters in the same decades across continents separated by months of travel. Then came the railways. The Liverpool and Manchester Railway opened in 1830. By 1850, Britain had laid 6,000 miles of track. The United States went from near zero to 9,000 miles in the same period. Russia, starting later, built the Moscow-St. Petersburg line, a dead-straight 400-mile route through forests and marshland, between 1842 and 1851. The construction speeds were extraordinary even by modern standards. The Great Western Railway in Britain, designed by Isambard Kingdom Brunel, laid track at grades and curvatures that required mathematical tables and surveying precision that shouldn't have been possible with the instruments available. Brunel's Box Tunnel, opened in 1841, runs for 183 miles in a perfectly straight line through solid rock, allegedly aligned so the sunrise shines through it on Brunel's birthday. The tunnel took 5 years to dig. The workers used black powder, pickaxes, and 1 ton of candles per week to see in the darkness. 100 men died during construction. The surveying, according to records, was done by Brunel personally using a theodolite. Across the Atlantic, the Baltimore and Ohio Railroad faced similar challenges and delivered similar results. The Thomas Viaduct, completed in 1835, spans 612 feet on 8 granite arches, each one hand-cut and fitted without mortar in the joints. It carries modern freight trains at full speed today, with no structural reinforcement. The engineering knowledge required for these projects appears suddenly in the historical record. The training institutions that would formalize civil engineering, places like the École Polytechnique in Paris, were producing their first graduates exactly as these mega-projects reached completion. The workers themselves leave questions. Canal navvies and railway gangs were predominantly unskilled laborers, farmers, immigrants, former soldiers. Yet they executed techniques that required understanding of hydrostatics, load distribution, and geological assessment. The foremen who supervised them, often promoted from the ranks, made decisions about tunneling angles, bridge foundations, and embankment compaction that modern engineers spend years learning. The knowledge transfer isn't documented. The training programs don't appear in records. The infrastructure simply emerged. By 1860, telegraph lines ran alongside most major rail routes in Europe and North America. The poles were spaced with mathematical precision. The wire tensioning accounted for thermal expansion. The relay stations positioned themselves at intervals that maximized signal strength using principles of electrical resistance that wouldn't be formally taught for another 20 years. And beneath it all, the roads. Roman roads are famous for their durability. The Via Appia, built around 300 BCE, still exists in sections. But the arterial road systems of the early 19th century, from the National Road in America to the Highland roads in Scotland, used layering techniques and drainage systems that closely paralleled Roman methods. Methods that had been lost for over 1,000 years. The timing raises questions about rediscovery, about inheritance, about whether the knowledge had ever truly disappeared, or simply waited in forms we're only beginning to recognize. The scale was unprecedented. The coordination was invisible. The technical execution was The United States offers the clearest view of the pattern because the timeline compresses into decades instead of centuries. In 1817, New York State authorized the Erie Canal. The route would cross rivers, valleys, and the Niagara Escarpment, a 65-foot elevation change requiring a technology that didn't exist in America at the time. Engineers proposed a series of locks based on European designs they'd read about but never seen. Construction began anyway. By 1825, the canal was operational. 83 locks lifted boats across the state. 18 aqueducts carried canal water over rivers and gorges. The longest, across the Genesee River, spanned 804 feet on stone arches, built without modern cement, held together by precision cutting and gravity. The economic impact arrived before the economy existed to justify it. Towns appeared along the canal route in perfect spacing, roughly every 7 to 12 miles. These weren't random settlements. They featured standardized infrastructure: warehouses, grain elevators, loading docks, and weigh stations built to uniform specifications before significant cargo volume existed. The town plans anticipated population densities that wouldn't materialize for 40 years. Buffalo, at the canal's western terminus, had 2,500 residents in 1820. 5 years after the canal opened, it had 18,000. The grain elevators built in 1826 could handle 55,000 bushels per day. The regional wheat production in 1826 was nowhere near that volume. The infrastructure predicted the economy, not the other way around. Rochester saw the same phenomenon. The city built a 7-story flour mill complex in 1829 powered by the canal's water flow. The mill could process grain for a population 5 times larger than existed in the region. Within a decade, that population arrived and the mill operated at capacity. This pattern, infrastructure before demand, repeats across American expansion. The national road began construction in 1811, running from Cumberland, Maryland, westward into the frontier. By 1818, it reached Wheeling, Virginia, crossing the Appalachian Mountains on grades that never exceeded 5%. Modern interstate highways through the same terrain struggled to match those grades with laser surveying and computer modeling. The road was built for Conestoga wagons, but its width, drainage systems, and bridge load ratings accommodated vehicles far heavier than existed at the time. When automobiles arrived 90 years later, the road required minimal modification for motor traffic. The bridges tell the story most clearly. S Bridge in Maryland, completed in 1813, carries the national road across a ravine using a double-curved design that distributes weight through geometric arcs. The engineering is sophisticated, too sophisticated for a frontier road project managed by surveyors with chains and compasses. Yet it stands, carrying modern trucks without complaint. Across the country, railroad construction showed the same anticipatory precision. The Transcontinental Railroad, completed in 1869, required surveying a route across 1,800 miles of unmapped territory. The Union Pacific and Central Pacific companies worked from opposite directions, meeting at Promontory Summit, Utah. According to the historical record, the two lines aligned within inches after crossing deserts, mountains, and plains with no GPS, no satellite imagery, no aerial reconnaissance. The margin of error was impossible. The coordination was invisible. The Central Pacific tackled the Sierra Nevada using Chinese laborers who'd never built a railroad. They carved 15 tunnels through solid granite, some over 1,600 feet long, using black powder and hand drills. The summit tunnel took 2 years and required workers to excavate from both ends simultaneously, meeting in the middle with perfect alignment. The technique is called heading and benching. It requires precise surveying to ensure both teams dig on the same vector. A deviation of even 2 degrees over 1,600 feet creates a misalignment of over 50 feet. The Chinese workers had no formal engineering training. The foreman had limited tunnel experience. Yet every tunnel met in the middle. Britain's railway expansion showed similar patterns, but with a detail that rarely gets mentioned: administrative uniformity. By 1850, British railways used standardized track gauge signaling systems and timetable coordination across dozens of private companies. This wasn't mandated by government until later. The companies simply agreed. They adopted common specifications, shared technical drawings, and built interconnected networks that functioned as a single system despite having no central planning authority. The Railway Clearinghouse, established in 1842, managed the financial accounting between companies but had no enforcement power over technical standards. Yet those standards emerged anyway, as if following an invisible template. The station architecture reinforced it. Victorian railway stations across Britain, from London's King's Cross to Newcastle's Central Station, share design elements that go beyond aesthetics. Platform heights, canopy spans, track spacing, and switching layouts follow patterns that allowed interoperability on a national scale. The buildings look distinct but function identically. This wasn't accidental. But the coordination mechanism isn't in the historical record. In the United States, the pattern appeared in grain elevators. By 1860, Buffalo had the largest grain storage capacity in the world. The elevators used standardized designs, vertical wooden structures with steam-powered bucket conveyors that lifted grain from ships, weighed it, and distributed it to storage bins. Every major Great Lakes port adopted the same system within a decade. Joseph Dart built the first commercial grain elevator in Buffalo in 1843. Within 15 years, identical structures lined the lakefront in Chicago, Milwaukee, Duluth, and Cleveland. The designs spread faster than information could travel, appearing in cities before Dart's patents were even filed. The electrical grid followed the same trajectory. Thomas Edison's Pearl Street Station in New York, operational in 1882, provided direct current electricity to 59 customers within a square mile. Within 5 years, over 100 cities in America and Europe had central power stations using near-identical designs. The distribution systems, underground conduits, transformer stations, metering systems, showed remarkable consistency across continents. The technical challenges were immense. Underground cables required insulation that wouldn't degrade. Transformers needed copper windings precisely calculated for voltage conversion. Safety systems had to prevent fires and electrocution. Yet cities implemented these systems simultaneously, with minimal catastrophic failures, despite having no shared regulatory framework. The telegraph network offers the most striking example. By 1861, telegraph lines connected the Atlantic and Pacific coasts of the United States. The wire stretched across empty plains, over mountain ranges, through territory controlled by hostile nations and tribes. The poles stood in perfect intervals. The wire maintained consistent tension. The relay stations appeared at mathematically optimized distances. The transcontinental telegraph took 4 months to build. The crew worked from both ends, stringing wire at speeds that required advanced placement of poles and insulators, meaning someone had already surveyed the route and positioned materials before the main crew arrived. The coordination required maps, detailed maps that showed terrain, water sources, and optimal routing through land that was supposedly unexplored. Those maps existed. They appear in railroad company archives and military surveys and private collections. They show detail that shouldn't have been possible without aerial observation. River courses, elevation changes, geological features, all rendered with accuracy that wouldn't be matched until satellite imaging. The explanation in the historical record involves ground surveys, indigenous knowledge, and exploratory expeditions. The timeline suggests something else. The infrastructure appeared too quickly, too uniformly, across too vast a territory to rely on incremental discovery. Whether this reflects inheritance or convergence, accident or design, remains open to interpretation. But the pattern holds. Infrastructure built before demand. Technical sophistication without institutional training. Administrative coordination without central authority. The systems didn't grow. They emerged. The word Tartaria appears on European maps starting in the 13th century. It referred to the vast territories of Central Asia controlled by Turkic and Mongol peoples, a geographic designation, not a unified empire. Cartographers used it as convenient shorthand for regions beyond direct European knowledge, the same way Indies once described everything east of the Mediterranean. By the 18th century, the term fragmented. Maps showed independent Tartary, Chinese Tartary, Muscovite Tartary, administrative divisions of the Russian Empire and Qing dynasty. By 1850, the word largely disappeared from official maps as more precise geographic and political terminology took over. The modern reinterpretation began online in the early 2000s. Researchers noticed architectural anomalies, examined old photographs of construction projects, and questioned the accepted timeline of industrial development. They pointed to the infrastructure patterns we've discussed, the canal systems, the railways, the road networks, and asked whether the 19th century truly built these systems from scratch or inherited and restored something older. The term Tartaria became a framework for discussing these questions. Not necessarily a literal empire, but a placeholder for a possible predecessor civilization whose physical remnants might explain the engineering consistency, the architectural sophistication, and the curious timeline compression of the Industrial Revolution. 3 interpretation models have emerged. The first accepts the conventional historical narrative entirely. The infrastructure boom of the 19th century resulted from genuine innovation, rapid knowledge transfer, and economic forces that incentivized massive coordinated investment. The architectural similarities across continents reflect shared European engineering education, pattern books that traveled with immigrants, and the natural convergence of solutions to common problems. The speed of development, while impressive, wasn't impossible, just difficult. The human cost was high, the economic investment enormous, but the achievement was real and earned through sweat and calculation. This model has institutional support, extensive documentation, and centuries of accepted scholarship. It requires no revision of established history. The second model suggests a recent reset. Something happened in the early 19th century, possibly related to the climatic disruption of 1816, the year without summer, caused by the eruption of Mount Tambora. Crop failures, famine, and social upheaval swept the globe. In the aftermath, the argument goes, existing infrastructure was repurposed and restored rather than built new. The canal systems already existed in damaged form. The railway routes followed older pathways. The buildings with buried first floors showed evidence of catastrophic mud floods that buried ground levels and required excavation rather than construction. This model treats the 19th century as a recovery period, not a creation period. The infrastructure wasn't built, it was uncovered, repaired, and adapted. The remarkable speed of development reflects restoration, not innovation.